I will rewrite the echelon's variational principle here. That we had a complete metric space, say, well, proper, but I mean, let me say in R, lower semi-continuous, bounded from below. That's all. You can also admit minus plus infinity here, but then this is a funny way to write things, but it's a useful way. And for any u in low energy sublevel, low if epsilon is small, there exists u tilde in X that satisfies the following things. The energy of u tilde is not larger. The distance of u tilde from u is small if this delta is small. And the u tilde is the unique minimizer of some perturbed problem. So you can control this, the slope of the functional there.
The left-hand side is negative. Should it be?
Yes, but because of this is, I mean, this is the otherwise it was, so it works like this. I see. So last time we proved this lemma that has very mild assumptions, mostly because we will use it to minimize functionals. So as a first application, and I mean it's almost one application, but let us start with the easiest case in which X is a Banach space. This is an example of how to apply this. E is a Frechet differentiable functional on X, bounded from below. Then we will use that lemma to say that any minimizing sequence for E, of course, minimizing sequences exist. So say UH in X, E of UH tends to the infimum. There exists another minimizing sequence, say U tilde H, that is close to UH and such that the derivative of E on the new sequence goes to 0. This is what I write. There exists a new minimizing sequence such that it is even better, but actually we will just need the fact that U tilde H is a minimizing sequence. And actually, this is what we will need in the applications, but it is not. Also, this third conclusion is interesting in some sense. In particular, in relation to what I said yesterday about the concentration compactness lemmata by П.Л.Чебышева, then when you apply those lemmata to concrete minimization problem, you can conclude, if you are lucky, that any minimizing sequence, for any minimizing sequence, this minimizing sequence is close to some other minimizing sequence that has some behavior. So in any case, also П.Л.Чебышева goes to a closed minimizing sequence. So how to prove this fact?
Here we need some additional assumption, yes? Such additional conclusion on utility. Yes?
Pardon? Yes, otherwise. For instance, utility H equals to UH is true. Individual. Okay, otherwise, so let me use this one. No, to prove somebody, the first lecture noticed that here we don't have a moduli, but I mean, now it will be clear that it is not needed. Okay. So how do you apply? You have this minimizing sequence, and you apply the Echelon variational principle for any h with u equals to UH, for any h fixed with u is equal to UH. Epsilon is equal, for instance, to epsilon h square, and delta something that goes to 0 slowly.
What is epsilon h?
Okay, you take h, epsilon h in such a way that the first requirement is satisfied. So, for instance, epsilon h, any epsilon h, for instance, the infimum minus infimum of a plus a of UH. Of course, if UH is a minimum, you are done. I mean, you can assume that this is positive. For otherwise, you just take U is equal to U tilde is equal to UH, and so you are done. I mean, we can assume that this is positive. UH does not achieve the mean infimum. Otherwise, we are happy. I will follow, and Sasha knows why, I will follow strictly the notes today. Okay. So we have that we find U tilde H such that those three requirements hold. And the distance for any h, the distance between U tilde h and UH is smaller or equal than delta. There's something that goes to 0, so this is squared. Sorry, our choice is this one. Perhaps. Yes. And so the third main, the most important thing is the U tilde H minus E of, oh my God, V is smaller or equal than epsilon h squared over epsilon h, but our choice. Epsilon h squared over epsilon h. So this also goes to 0. And then is this one. This is the distance. And then, okay, the distance of u tilde h from V, that's for any V in X. So we want to estimate this in its appropriate norm. So for any W different from 0, say of normal arm, we apply this last important thing with V equals to, as usual, u tilde h plus t w, t is close to 0. And what we get is that E of E tilde h minus E of U tilde h plus TW is smaller or equal than, so this is, of course, in this case, the norm of U tilde h minus W. This is the distance in the Banach space. So this is, and here is the point, the absolute value of W. Here we are applying the equivalent variational principle in a Banach space, so this distance is the norm. See, I'm not sure I will be. I feel very well, but I'm not sure I'm very well. So because of this absolute value of t, you can see, take the limit as t tends to 0 from the right or to the left, from the left. And this goes, if you take t going to 0 from the left, then this goes to minus the derivative of the energy in U tilde h applied to W, while if you go from the left, you obtain this with a minus sign, with the opposite sign. In any case, this implies that, but since the functional is Frechet differentiable in any point, then you indeed have proved that the absolute value of the derivative of the functional applied to W in absolute value is smaller or equal than epsilon h, the norm of W in the Banach space. This means, by definition of a norm in the dual, that the norm of this in the dual is smaller or equal than epsilon h that goes to 0. Is it fine? This is for t. No, while this, I guess, is UHW as t goes to 0 from the left. It should be like that. So in any case, the you indeed are estimating the absolute value of the derivative applied to W. Do you agree? Well, the second application is essentially that one we will use. It's essentially the same exercise. Only we have that E is not bounded from below. You don't want to minimize E on a Banach space. You want to minimize E on a smooth manifold. contained in X. So assume that X is a Banach, and assume that E and G are, for instance, Frechet differentiable functions. Put M, the set of V in X, such that G of V is equal to 1, for instance. And as usual, you assume that at every point in M, you have a normal direction to M. So you are assuming that G prime of V is different from 0 for any V in M. Is this what you need in this? I haven't fantastic. I haven't write this here. That's why I haven't write this. Because perhaps. Okay. Well. Now again, let and assume, of course, that the infimum of the functional E on the constraint M is is greater than minus infinity. So E is bounded on the constraint M. And so more or less the same conclusion holds. That is, for any minimizing sequence, UH, there exists a new minimizing sequence. So it is a sequence in M. Yes, of course, this is needed, and a minimizing sequence in M. And there exists a bounded sequence of numbers, real numbers, such that, as usual, you gain something, you win something in the energy, as usual. The norm of u tilde h minus UH goes to 0, and this sequence of elements in the dual goes to 0 in the dual space. So more or less, it's the same. It's the same result. You know that from the Lagrange pardon? Yeah, you know from the Lagrange multiplier theorem that if you are able to find the minimizer for the energy E on the constraint M, then that means that somehow the form E prime in the minimizer is orthogonal to the constraint M. That is, this is the Lagrange multiplier theorem. That is, E prime in a minimum point is proportional up to some real lambda to the derivative of G that gives a constraint in the minimum point. So this means that UH almost is solves the equation for minima, the variational equation for minima of the energy E on the constraint M. And so first let me erase it. And then I will use actually we start as before. Actually, I will prove this not in this general setting, just to avoid the computations. So now I will take epsilon for any h. We'll take in the Echelon's variational principle epsilon h such that epsilon h squared is, say, the infimum of something close to this infimum on M. And then more or less, let me assume this way. Assume that there exists some p greater or equal than 1, such that g of say t v is equal to t alla p times g of v for any real positive, say non-negative. So we assume that in addition that G is positively homogeneous of degree P. This because, one, this allows me to simplify the notation. Two, it's not so terrible. I mean, what only I need that I can project, this is M, I can project a neighborhood of M onto M. I can do this always because of this assumption. Okay, so this is just to simplify the facts. Actually, I will use this second application of the Echelon's variational principle always and only when G is some p power of some norm of V. So I will actually use always this application under this assumption. G will be example some norm to the power p, for instance, in some norm y. Okay? So what I say is that if G is positively homogeneous of some degree, then I can write explicitly this projection. That is the only thing I need. I project, for instance, this neighborhood of the constraint M onto M by putting P of V is equal to G of V to the minus P V. Let me think if it is G sorry. Minus 1 over P. Okay? This is an extra assumption for the moment, but for this application. The only fact I need is that I can take a neighborhood of M. In this case, in this simplified case, the neighborhood is this one. And I can construct a projection P of this neighborhood into the constraint. Nothing more. Okay, now so I apologize for those very simple computations, but this is the best I can do today. I'm a little bit sick, not so much, little bit. Now the remark M is closed for sure because G is Fréchet differentiable, then it is continuous, so M is closed, and this is an open set. And since by standard rules, I can compute this derivative that is minus 1 over p It seems to be so long. This is for any v in this neighborhood of m, but if v is in m, then everything is very simple, because g equals 1. Sorry, perhaps I have some plus here. Why minus? I don't know. So in essence, this is the projection, in some sense, the projection of the Frechet derivative of this function p on the tangent space to m that exists because I have a normal direction. That's fine. Okay. This is just a computation. Then we apply the Ekeland's variational principle with the above choice of for any a. No. In CISA they have something that you push down this that goes up there, but for sure they are weaker than Russian people. I apologize with my colleagues in CISA. Okay. So I apply the Ekeland variational principle in this way. And I find, as before, why did I erase it? As there exists u tilde h, well, in M, because now I apply the Ekeland variational principle for E on M D. D is the distance that is indeed the norm on the Banach space, and M is this closed subset of the Banach space X. That means that for sure this is a complete metric space, because M is closed. And there exists a sequence in M such that you win perhaps something in the energy, and E of u tilde h. Now let me take directly here V. Let me write directly V as u tilde h plus tw, as we did before, with w in x fixed. No. No, I write like that, and then I now that holds for every v, not in x but in m. If I put the large inequality here in m, because I'm applying the Ekeland variational principle for this functional, which is defined only on M. Now, as before, I have to choose suitably V in order to prove this fact. How to choose V in M? I take this is M. Here I have u tilde h. This is something perhaps u tilde h plus TW for some, I mean, this is an infinite dimensional draw, for some fixed W, to fixed W in X, and then I project this one here. Here I find the point P U tilde H plus TW. This is something you can always do in this general case, but in the under those additional assumptions, everything is very explicit. So I will apply this conclusion in the Ekeland's variational principle with some V choosing like that. V for sure is in M by construction. Okay. And so we find what? EU tilde H minus E of projection U tilde H plus TW. Oh my God. I have large classes, so I write too large. Is smaller or equal than epsilon h, the norm of U tilde H minus projection of U tilde H plus TW. Okay, I can write it in this way. Here I divide by T inside the norm, and then I have to push some moduli of T there, and here I divide by T and put some T outside. Now here you are computing the rapporto incrementale. You are trying, when you let T goes to 0, this approaches what? The derivative of the composite function P composed with E at the point U tilde H. It's fine? So this one goes to minus because you have inverted this. The derivative, this as this goes to 0, if you want, goes to the adesso sbaglio, lo so, P' di U tilde H picchietta W. I don't know if this yes. Let me write what it is. Oh, this, since U tilde H is in M, this is U tilde H. And here is P prime. It's not very easy to write in this. Something is G prime of U tilde H. It is written here. Why should I? So, okay. Some UH is missing here. So I use some linearity, and this is a number, a real number. No. G prime, no. I have to write something more. 1 over P. I use the linearity of this form applied to U tilde H times G prime of U tilde H in W. Okay, and then I also have E prime of U tilde H computed in W, just by linearity. This is a real number. I call it lambda H. Since, UH is surely bounded. Is surely bounded because for every bounded, for every bounded minimizing sequence, say, I assume now that UH is bounded, then also U tilde H is bounded, and so Weierstrass theorem tells you that this is a bounded sequence. Okay? Oh my God. And then I only need the derivative by the right-hand side. In writing this in text, it's not so long, but at the blackboard it seems it is very long. And then, of course, that is easier. U tilde H minus P of U tilde H plus TW, which is in the right-hand side, goes to what? To P prime of U tilde H computed in W, as T goes to 0. Okay? This goes to P prime computed at U tilde H computed in W. U tilde H is in M, so we can use this formula like 1 over P G prime of U tilde H computed in W. U tilde H, which is here, minus W. Now, U tilde H is bounded, G is continuous functional, so we can say that this is smaller or equal than C times, because it's here and here, the norm of W in X. Can you read? It's more or less. No, some tedious, but it's easy, but tedious computations. I don't know why I'm doing that, actually. Easy computations, it's what is really hard is to write them in the blackboard. This is really hard. Okay? But then in your notebook, it's much easier. Okay, and then, so we glue together the things is that T, let me write it another way, T times something, which is lambda H G prime of in UH. I'm writing this in a slightly different manner. E prime of U tilde H computed at W plus something that goes to 0, computed at W. And this, something that goes to 0 does not depend on W. Okay? This is smaller or equal than as before, the absolute value of t, epsilon h times this constant times the norm of W. In some sense, this is what I said. But here you have t, and here you have the absolute value of t is more or less as before. Then but you know that all the functionals here are Fréchet differentiable. So you divide by t positive, and you have a sign. You divide by t negative, you have the opposite sign. And as a matter of fact, you have that since this holds for any w in x. You have that what you want. Now it is really too long, this proof. I apologize. It's a too, I mean, plus something that goes to 0. Epsilon I is 10a. No, it's like that. When at the end of the story, t disappears, of course. So this goes to 0 as desired. It's just computations of derivatives, of first year derivatives. I mean, we all compute directional derivatives, so the derivatives of one real variable in t. Okay, so it happens that, I apologize, this will be, it was too long. I suggest to repeat all the computations by yourself if you are interested somehow, because they are very, 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 very easy. Nothing. Please, questions? Something you don't believe? Mm-hmm. I will stop. I will make a break here because. Well, I will not prove for sure after this long and boring proof. Plenty of computations. I will not prove, but I will at least mention some technique that was originated indeed by some papers by Mitidieri. But I will mostly talk about a paper by D'Ambrosio, Lorenzo D'Ambrosio. So we go back to the argument how to get inequalities. And this is essentially a divergence method to get inequalities with a candidate for the best constant. Somebody asked me when I mentioned the Allegretto-Pirpenbeek idea, well, in that case you have an inequality, but you have no idea about which is the best constant. Generally speaking, the divergence method, as described in this paper by D'Ambrosio, gives also the best constant. We shall see in the second part of this faticoso, come si dice faticoso? Lecture. Definite, no, tedious is noioso, tedioso, so heavy. Now, this is. I just want to say this because I fear the students will escape for the next second part. No. I will immediately, don't escape, please. I will immediately change. Okay? Here is the black. So I will only state the main result by Lorenzo D'Ambrosio, I have to say that I will deal with the P Laplacian cases. Let me see. What's the P Laplacian? So you take P, say, greater than 1 for safety. And minus P Laplacian of phi is the minus divergence of nabla phi to the P minus 2 nabla phi. Is this operator. So I will present his result only for this operator, but Lorenzo D'Ambrosio noticed that his technique holds in very general settings for very general differential operators, also on manifolds, on hyperbolic spaces. I have a list here. He presents examples for the Bowen-de-Grushing operator, Heisenberg gradient or Laplacian on the hyperbolic space, and more generally in Carnot group, Heisenberg-Reiner differential operator gradients. I mean, very general technique that gives you, first of all, helps you to prove inequalities, and generally speaking, it gives you the best constant. Generally speaking, it tells you when the best constant is achieved or when it is not achieved, generally speaking. So the idea is the following. The ingredients is, this is Rn, but you can be much more general bounded domain, in any domain. N greater or equal than 1. A is a real exponent. Phi is a non-negative measurable map. So I need to say that some power of phi is a super solution of the equation minus Laplacian P of phi sigma times some constant is greater or equal than 0. I want to say this one. This is an assumption. Let me, but in some distributional sense. So before saying that, I need to ask that phi has some properties. I mean, you have to write this operator in a distributional sense, at least. So the first assumption, these are regularity assumptions, is that phi to the power A is given, is in L1 log of omega. Well, this is not to say, these are two assumptions, are not to say that phi is a super solution of this. I have to write those two requirements since these two functions enter as weights in the inequality I will write down at the end. So this is the main assumption in some sense. There exists another exponent, an exponent sigma, which is not 0 and which is not A over P minus 1 for some reason, such that first I write the equation C. Let me copy. Minus sigma, I don't know if sigma is positive or negative. Sigma P minus 1 minus A. Please let me know if you don't see very well what is written here. This is a constant times this operator is greater or equal than 0 in the distributional sense. No, in the distributional sense, weakly. that means that sigma p minus 1 minus a, the integral, the operator non ci sta, phi sigma minus 1 p minus 1 gradient of phi p minus 2 gradient of phi dot gradient of eta is greater or equal than 0 for any eta. So this is not, I was wrong. So not in a distributional sense, but in a little bit stronger sense, that is a weak sense. Look at the P Laplacian is this one. So I have already computed the derivative of gradient phi to the power sigma. Because of this, so you have this power, and because of this you don't have any more sigma, because the sigma squared is positive, so I erase it. Of course, in order to be able to write this, I have to ask as an assumption that this function is in L1 log of omega. So what is the function star? The function star is this function. Just to be able to write down this.
The sign of eta.
As before, eta greater or equal than, for any eta greater or equal than 0. Otherwise, it's quite a strong assumption, say. Well, all those are assumptions, but actually you just have to see that some power of phi of sigma satisfies an equation. Generally speaking, it may happen that phi to some power, the phi that you are using is indeed a smooth function in some omega you are interested in. The conclusion is, if the above assumptions holds, then it holds that the integral on omega of phi to the power a gradient of u to the p is greater or equal than lambda, some lambda, constant lambda, that depends, of course, on omega, perhaps on omega, I don't know. Here there is another mistake. Let me write the integral. Phi a minus p gradient phi to the power p u to the power p, that holds for any u in C infinity with compact support in omega, and the constant lambda is the supremum of all the numbers like sigma p minus 1 minus a over p to the power p, such that sigma satisfies all the assumptions in the 2. Of course, you might find more than one sigma that satisfies 2. In the conclusion here, sigma does not appear. It's just a tool. And of course, you are interested in taking the largest possible constant lambda. Generally speaking, in all the interesting examples, this is the best constant, the best possible constant you can put here. Generally speaking, it holds that there are two possibilities. The first one is that this lambda is achieved by some sigma, some best sigma, and you could find that phi to the power sigma, that special sigma, is in the right energy space, and it achieves the best constant. Or, if it is not the case, this constant is not achieved. Generally speaking, this technique by D'Ambrosio tells you which is the candidate best constant and tells you when the best constant is achieved or not achieved. Really, I will not, in view of the previous experience, the proof is really very, very simple. You can do it by yourself. You call rho this constant here. And essentially, the proof is use phi as we did something like we did to the power p as test function. Where u is C infinity with compact support in omega fixed. Well, more or less you do it this way. You can do it this way with some care. We have to check that everything makes sense. You can do it actually. If p is smaller than 2, then it's better to approximate this function. But if p is larger than 2, there are no trouble to use this test function and make some computations and just have the conclusion. Okay? So let me show you just 2 examples. One is an example of an inequality that I don't know why it's, I mean, it can be generalized. It has been proved by Leray in 1933 while he was studying some problem in hydrodynamics. You know that the hard inequality, generally speaking, say that, take for instance, not all functions u. Well, what actually it calls for any function. Let me just take the invariant case. We already proved this in several ways, by the way. And of course, this B is the unit ball in Rn. N is greater or equal than 2, because for n equals 1, this is not connected set. So this is X. Of course, this is really not interesting at all when n is equal to 2. And because if n is equal to 2, this is 0. The Rayleigh inequality is an inequality of totally different type with respect to the so this is the unit ball in R2, exactly the unit ball in R2. It's of different nature, but essentially it can also be proved via one-dimensional hard inequality, actually. So in 2 dimensions, this way does not work well because it is not locally integrable. That's the reason why. While you take a slightly better weight in the origin, and you win some inequality. Notice that in contrast, this weight is not so nice when X is when you're approaching the boundary of the unit ball. In essence, those two inequalities are different. in deeply different because this is the dilation invariant inequality. Finally, this enters in the title of my course, dilation invariant inequalities. It means that when you compose you with dilations in Rn, this has the same rescaling property like that, while this is not the case for this inequality. And to prove this inequality, you just take, I will not make a computation. Phi of, so you take P equals 2 in the D'Ambrosio theorem, phi of x is equal to minus the logarithm of x of the radius. And of course you take A equals 0. You just have to see which are the sigmas you can use. This is the only exercise.
In this case, the constant is the best.
Pardon? The constant is the best and it is not achieved.
There are a function on which it's equation?
No.
There are
No, no. I mean, this inequality holds with strict sign if U is non-zero. U actually in C infinity with compact support in the ball. Actually, by density, also for functions in H1 0 of the ball of the unit disk, but it is never achieved. No function with finite with gradient in L2 can reach this constant. Another proof is with the Emden-Fourier transform. I already mentioned. Try to compute this integral, and this integral via this transform, and see how to write this in terms of g and how to write this in terms of g. This is a nice exercise. Okay. Then you can also perhaps I should use this. You can also use the for instance, this theorem, but we will prove in another way, to prove the inequality, the hard inequality with cylindrical weights. So let me change a little bit now notations. From now on, and more or less, starting from now until the next week, the end of the course. I, of course, take this just an example. So I'm still working in Rn, but I'm looking Rn as the Cartesian product of some Rk times Rn minus k. So in this, pay attention, this in the inequality I wrote up to now, x is the variable of u. Now I apologize for this, I will change notation, you have to pay attention. So this is what? This is the distance from the origin, okay? Now I denote, from now on, I denote because my notes are written in this way. I cannot switch all the notation. Not more x, but xi, and x, y. Pay attention. X is k of the coordinates of y. Okay, so the norm of x now is the distance of the point xi from the set of point from an n minus k dimensional set. Sorry, this is capital and this is capital, let's say. So in that case, I was taking k equals n. Now k, so up until now k was n. Okay, for instance, if k is equal to 1, now I'm looking Rn as R times Rn minus 1. And so this x is the distance. No, vice versa. This is Rn minus 1. Let me take this one. Is the distance, for instance, if you take only k equals to 1 and positive, you have null space and you have the distance from the half space. That I say this because it has some relevance. So pay attention from now on, all the integrals are in the c variable, but the weight is the weight in x, part of the variables. And the hard inequality with cylindrical weights states that I also have p greater or equal than 1, states that for any a in R, so this please look. Here I have to put the absolute value. So this is what I claim. In this generality, U, it's better to ask that U vanishes on a neighborhood of the set x equals 0. So
everything except that.
pardon?
Everything except that set.
Yes, it has. It vanishes. It vanishes in a neighborhood of x equals 0.
Yes,
Yeah,
yes.
but it's written on the opposite.
Perhaps, yes, surely. Surely, it is written exactly the opposite. Why? Because otherwise the weight in the right-hand side, for sure, is not. It may be not integrable, but it holds for any u in C infinity with compact support in Rk times Rn minus k if A is greater than P minus K. So, as an exercise, you can try to prove this by using the D'Ambrosio theorem, and in that case, you take phi is equal to the modulus of I, and then you have to look for the right sigma, the right exponents, and so on. But since okay, we also know already this inequality, for instance, for A equals 0 and P equals 2, and also for A not necessarily 0 and P equals 2. I have another proof of this. I will sketch it. One of the possible proofs is the theorem by D'Ambrosio with this. But I want to make this proof by assuming first that k is equal to n, and then I will tell you a story. It is essentially the D'Ambrosio result. I mean, also this proof, I follow the D'Ambrosio idea, okay, which is not really such a new idea. But there are so many ways to prove it. First of all, I don't know why here there is notes of course given in CISA. First, assume that k is not is n, and that a is not p minus 2, and that p is not 1. All those things.
Maybe plus p minus n? Why p minus 1?
Because, I mean, you can choose as many. For instance, equal 0, greater or equal than 0, less or equal than 0. You can choose, you have a variety of choices. And I choose this one. So another exercise is try to with different because no, it's not 0, of course, it's something. Not 0, so something is something. So k is equal to n, that is n is equal to k, so I will prove this in Rk instead of n. And then I will tell you a story. So this is better, since this is Laplacian in k dimensions, which is equal to n, by the way, for the moment. I mean, the problem that I am asking, for instance, a different from p minus 2 is really not a problem, because I have explicit constants, so I can let a go to p minus 2 if it is. This is plus Laplacian of that is equal to this one. Of course, this is in a strong sense in Rk minus 0. K is equal to n for the moment. And then I test with u fixed, like that. And I test with u to the power p. So that, you know, this choice is due to the fact that here I have almost already the constant. Not so nice. And I also take the absolute value, actually. I am correct. Boo. The story is always the same indeed. Over So this is smaller equals something erases. So actually this is not so important, but otherwise I would have write 0 is equal to 0, not, without this assumption or something. So this is x a minus p plus 1, and then u to the p minus 1 gradient of u. It's something similar we already done in the first lecture for p equals 2. And then you simply take some of those you put with gradient of u, some of those you put with u. Use Hölder inequality between, say, first p greater than 1. P is greater than 1, so you use the Hölder inequality between p and its conjugate exponent. And the computations are fine. The exponents are fine to make okay, then you simplify something with.
So I think P also should be the right hand side.
Some P, of course. P is missing here. P is missing here. Thanks. Because then you divide this by P. You have moduli of k minus p plus a over P. I mean, you have already concluded because you divided this by P. Non si vede? But I mean, I just taking this, put it there. Then from 1 here I pick out this, and 1 minus p minus 1 over p is equal to 1 over p. Okay, so you have this integral. It's the same integral as before. This is just because I divide by this. And this is smaller or equal than the remaining part. Even if it is not completely readable, I mean, it's really a trivial computation. And then, and of course, I approved the hard inequality. Now, to capture the case when A is equal to p minus 2, for instance, and p is not 1, you just take a epsilon is equal to p minus 2 plus epsilon, hoping it is not 1. Then this is not p minus 2. Then you can write down the hard inequality for a fixed u. So this is A. Because in this moment A is p minus 2. It is possible to follow, even if it's not well written. I mean, but this is really... We can apply this inequality because we already approved it. What I'm saying here is that even if for the moment we have excluded the case A equals P minus 2, since we have an explicit formula for the Hardy constant, it doesn't matter. P minus 2 is always very close to something which is not P minus 2. And then you let epsilon goes to 0 to get an equality you want. In the same case, when P is equal to 1, you first apply the Hardy inequality you've proved with P is equal to 1 plus epsilon, pass to the limit, and you can check that that inequality holds also for P equals 1. Okay, that is always a worrying case. So this completes the proof for the, say, when the weight has a spherical symmetry, and how to prove the theorem. This is really difficult case. In fact, when K is smaller than N, you first write down the Hardy inequality you have just proved in RK. So in RK, because we proved this in RK, so these are always integral in the x. The x or the xi is the same, so we are allowed to write down the Hardy inequality in RK. The right constant, k minus p plus a, these are absolute value. So these are integral in the x in RK. To get the inequality in Rn, you just have to integrate in Rn minus k, because everybody knows, everybody knows Fubini's theorem. And this is the story I want to tell you. There is a very largely cited paper, really a wonderful paper, deep paper, by Badiale and Tarantello, a Sobolev-Hardy inequality with applications to a nonlinear elliptic equation arising in astrophysics, or 200 of citations. You will say archive for rational mechanics and analysis, 2002, in which they have n equal 3, k equal 2, and they use pointwise estimates, 2 or 3 pages, to prove the Hardy inequality with cylindrical weights. That's sure. That is the Fubini theorem. That is the story. However, it is a nice paper. Okay. So of course I made an epsilon of what I was planning. And so for this lecture I will just mention some remarkable facts of this Hardy inequality. The next step will be those I called semi-linear or non-linear inequalities. This is linear, in the sense that here I have P and then I have P. And you see that it doesn't matter, the fact that we have a cylindrical weights instead of a spherical weights, it's really a triviality for linear inequalities. When we will deal with P, Q, the difference will be remarkable. This is the reason why I insist with cylindrical weights. And who actually understood, firstly perhaps, the deep difference between, we will see there will be deep differences between the spherical cylindrical case is for sure Professor Maz'ya. Remarks about this inequality. This is an dilation invariant inequality. This is the first and the first remarkable fact about this inequality. I have to. What does it mean, dilation invariant inequality? It means that if you apply oh, it's 8. Oh my God. I don't know. I went on so slowly. I'm so sorry. No, I will not start. Just say. I will just say. Which will be the next remarks I will do on this. So, what does it mean, dilation invariant? It means that they rescale in the same way. And this is, of course, trivially true, must be true, because those are inequalities on Rn. It means that, for example, if you call C this constant, if you are hoping that for some B, you can find a positive constant such that this inequality holds for any u, it means that surely this integral must have the same rescaling properties of this integral. It means that B is equal to A minus P. This will be the first remark. No other chances you have. The second is something Dalmaso, I've learned from Dalmaso several years ago, is that when you have two integrals that rescale the same way, perhaps some inequality among them is true, just as a philosophy. It is not always true for first order, not for higher orders, for instance. The next, I will prove that there are many ways to prove that this is the best constant, indeed. There are many ways, and I will use to prove that this is the best constant another group of transforms that acts on radially symmetric functions, and that make a radial function concentrate into the boundary of the unit circle. Then I will notice that this holds for P greater or equal than 1. The case P equals 1 is always really, it's better to avoid. Again, perhaps it's not of my opinion. Why? Because spaces that have 1 here and then something else are not reflexive, Banach spaces. Something first and then 1. L1 is not reflexive, W11 is not. And this is terrible because if you want to solve a minimization problem, then what you do is to apply the direct method in the calculus of variations. Take a minimizing sequence, prove that it is bounded, and if your space is not reflexive, you finish there. Sometimes not. But I insist on the fact that for P equals 1, because it turns out that for P greater than 1, the best constant is not achieved in any reasonable energy space. While for P equals 1, the minimization problem is really easy. An incredible large number of functions achieves the Hardy constant for P equals 1. So we are not in trouble with minimization problem in a non-reflexive Banach space, because minima exist. And then we'll, so this will be the beginning. I could skip it, the remarks are exercise. Try to see which are the functions that achieves the best constant, Hardy constant with P equals 1. Then I will see you on Saturday. Okay? Okay. Va bene. Bon. It seems I'm still alive. It's no, please.